So there were a few things that we had to finish up in regards to both sections 4.1 and 4.2. So on 4.1, this is what we had left off at. So let's go ahead and take a look at that first. It combines function notation and exponents. So here it's asking for f of x. I see my f of x equation here. Well, it's asking me for f of 5. So that means use the f equation, but plug 5 in for x. So I plug 5 in for x there, so that's 3 to the 5th. So doing that on my calculator, 3 to the 5th, not 335, but 3 to the 5th is 243. So f of 5 is equal to 243. Then we have h of 2. That means you use my h function over here. And what am I going to plug in for t? I'm going to plug 2 in for t. So that becomes 4 times 3 squared. Now, because of order of operations, I know that I have to do the exponents before the multiplication. So 3 squared first. So h of 2 equals 4 times 3 squared, which is 9. And then h of 2 is equal to 4 times 9 is now when I can complete that multiplication, and that is 36. So again, function notation, but in the context of situations where exponents are present. The last thing we had here was scientific and decimal notation. Some of you will remember scientific notation from a science class you took, or even from Math 70. I believe they touched on it really quick, or some context you've had exposure to it. So here's what it's all about. 5.6 times 10 to the 7th is a shorthand way of writing a larger number. Now, 10 to the 7th is 10 times 10 times 10 times 10 7 times. So if I look at what happens, if I do 5.6 times 10, it becomes 56 times 10. It becomes 560 times 10, 5,600. Well, if I keep doing this, that was 4 times, 5 times, 6 times, 7 times. That gets me to 5600000. What you'll notice is what happened is the decimal point essentially got moved over 1, 2, 3, 4, 5, 6, 7 spaces. Because every time you multiply by 10, the place value gets bumped 1 up. So 5.6 times 10 to the 7th is actually 56 million. Now we can do the same exact thing here, except it's a negative. So what I would do is, just like you saw the pattern here, the 10 to the whatever moves the decimal point, but since it's negative, it actually moves it the other way. So this would become 0.00000046, because that decimal point moved over 1, 2, 3, 4, 5, 6 spaces. So 0.00000046. Back to here, I've got times 10 to the positive 3, so that moves over 1, 2, 3 spots to become 9,300. And then down here, moving the decimal point to the left, because it's a negative exponent on the times 10 to the negative 4th, becomes 0.000726, because I moved it 1, 2, 3, 4 spaces to the left. Now we can do this backwards as well. You'll notice here we're going from decimal notation back to scientific. So when you see the times 10 to the whatever exponent, that is scientific notation. Decimal notation is what we're used to, what we're looking at in these numbers right here, but we want to put them in scientific notation. So to do that, I have what I'm going to do is I look at my very first non-zero number. It's a 4. So I'm going to go 4 and then put the decimal point right after that, 4.35. Now, I have to ask myself, times 10 to the what? Well, the 4.35, what would I have to do to that decimal point to get it back to where it belongs? Well, I'd have to move it to the right 6 spaces. So it's going to be times 10 to the 6, because I would have to move it to the right 6 spaces to get back to the 4,350,000. In this example here, very first non-zero number is the 5. So I'm going to go 5.3. I put the point right here. In order to get back to where I was, I would have to move the decimal point 1, 2, 3, 4, 5, 6 spaces, but to the left. So 5.3 times 10 to the, because it was to the left, negative 6. If you're writing a decimal, or if you're writing a number in scientific notation that you know is a really small decimal, you know that the exponent's going to have a negative on it. Whereas if you're writing a really big number in scientific notation, you know that it should have a positive exponent on the times 10. So again, here's a big number. 9's the very first, so 9.32. And this is going to be times 10 to the 1, 2, 3, 4, and 5. That's how many spaces I'd have to move it over to get back to the 932,000. Last but not least, we've got 3.2 times 10. Okay, the first non-zero number is the 3.2 times 10 to the 1, 2, 3. But it's a small number, right? So I know it's going to be negative 3. So there's decimal and scientific notation and how you convert back and forth between the two. That finishes up section 4.1. Now we've got section 4.2. There was one problem that we didn't get to in section 4.2 that I said that I would get to. So here it is. We've got a fairly decently sized exponential expression, or expression that contains exponents that we need to simplify. Now, what I notice is this: the parentheses are not around both top and bottom together. The parentheses are around the top, and those have an external exponent of 1/2, and then there's separate parentheses around the bottom. So I can't combine things top and bottom yet until I bring these exponents in. So let's do that. That 1/2 belongs to everything. So that's 81 to the 1/2 times b to the, now when we bring an exponent in, so it's b to the 6th to the 1/2, it's these two numbers multiplied. So 6 times 1/2, half of 6 is 3, times c to the, now 20 times 1/2 is 10. Good, and that's divided by, now this 2/3 exponent goes in. So that's going to be 27 to the 2/3 times b to the, well, what is 12 times 2/3? Doing it over here, 12 times 2 over 3. I could make that a 12 over 1. So 12, and then remember multiplication of fractions, straight across the top. 12 times 2 is 24. All over 1 times 3 is 3. And this actually simplifies. 3 goes into 24 8 times. 8, 16, 24. So this just becomes b to the 8th. And then we have c to the, well, that 9 gets multiplied by the 2/3. 9 times 2 is 18, divided by 1 times 3 is 3. Now 3 goes into 18, let's see, 6 times, 6, 12, 18, yeah. So that becomes c to the 6th. Okay, so things simplified pretty well. Let's take a look at what we've got here, though, with the constant numbers that have rational exponents. So 81 to the 1/2. Remember that the denominator of the exponent is actually a root. So that's actually the square root of 81 to the 1st power times b to the 3rd, c to the 10th. All over, again, the denominator becomes the root. That's the 3rd root of 27 squared, b to the 8th, c to the 6th. Now what is the square root of 81? What number multiplied by itself equals 81? 9. 9 times 9 is 81. And since it's to the first power, it really doesn't matter. It just stays a 9. So that's 9 b to the third c to the 10th. All over. And now this one, 27 to the third power, to the third root. What value multiplied by itself again equals 27? I believe it's 3. 3 times 3 is 9 times 3 is 27. So the third root of 27 just becomes 3, and then 3 is squared. You got b to the 8th, c to the 6th. So that actually becomes 9b to the third, c to the 10th, all over, look at that, 3 squared is 9, b to the 8th, c to the 6th. So we can see though that now I can start canceling things out top and bottom. 9s cancel each other out. And then I'm left with b to the third over b to the 8th. So top exponent minus the bottom, 3 minus 8, so that's b to the negative 5, times c to the, 10 up top, 6 down below. 10 minus 6 is 4. Now I have a negative exponent, so that b value gets moved to the denominator. So this becomes c to the 4th in the numerator, because I don't move the c, the exponent is positive, all over b to the positive 5, because when I move the b down from the numerator to the denominator, the exponent goes from negative to positive. So all of that simplifies to c to the 4th, b to the 5th. So that wraps up what we had not quite gotten done in class. We'll see you guys Saturday.